Hello, and welcome to another episode of Engineering Examples. Today, we'll be going over an ideal Rankine cycle, also known as a reversible Rankine cycle. So jumping right into it, in a reversible Rankine cycle, steam leaves the boiler and enters the turbine at 4 MPa and 400 degrees Celsius. The condenser pressure is 10 kPa and exits as a saturated liquid. Find the thermal efficiency. So first, what I like to do is draw a quick schematic in order to properly visualize the problem. From this, we can also determine where Q in is, where W out is, Q out, and work in. Next, I like to identify quickly what the components are and identify state points. Keep in mind, these numbers can be different as long as they're consistent. Next, I like to draw a quick TS diagram. Keep in mind there's two pressures here because we have one turbine and one pump. This will be the 4 megapascals and 10 kPa. Most points can be quickly plotted on this TS diagram, except for state point 2, as we do not know where state 2 lies, whether it's in the mixture region or superheated. So the easiest point to start will probably state point 1, because we know the temperature and pressure here. So from this, we can easily go to table A4 and pull the enthalpy and entropy values, so H1 and S1. Next, we can go to state point 2, and here we know that S1 equals S2. This is because it's stated that the cycle is reversible, also known as ideal, both meaning the same thing, that there's no entropy generation. So if we go to table A3, which is the mixture table, or what is contained within the vapor dome, what we want to do here is determine what SG is. And the reason we want to do this is because we want to see how it is compared to S2. And in this case, SG is larger than S2, therefore we are in the mixture region. We can then compare S2 to the saturated liquid and saturated vapor to saturated liquid to find out the location of the point in the mixture region. We can then go to table A3 again at the same pressure of 10 kPa to find the enthalpy values here, the saturated liquid and saturated vapor. We then take the saturated liquid and we add that to the difference between the saturated liquid and saturated vapor multiplied by our X value, and this will determine the enthalpy at state point 2. Next, we can move on to state point 3. As seen before, this is the saturated liquid point that comes out of the condenser. So this is relatively easy. We've already obtained this value above, actually. Next, we'll move to state point 4. This will need to use a different technique. So we'll actually find the work into the pump first. We can use the pressure difference, making sure that this is in kPa, must be in kPa. And then we also take the specific volume at state point 3. We can also obtain this from table A3. And we multiply these together to get the work into the pump. After having this work into the pump value, we can then determine H4 by simply adding it to H3, because this is what has occurred to get to the next state point. Therefore, now we have all the enthalpy values at all of our 4 state points. The next step will then just be to find the turbine work. And we can determine this by going above and looking. So we go from state point 1 to state point 2. Therefore, we just subtract H1 from H2. We already had just calculated the work of the pump above, so we can get that value. And lastly, we'll need to determine Q in. So going back to the schematic above, we can see that is H1 minus H4. We just simply subtract H1 from H4, and we have our Q in value. Next is the thermal efficiency, which is just the work of the turbine minus the work of the pump over Qn. And we can see that is 35%, which is a fairly reasonable value. Thank you for watching. I hope you gained some valuable knowledge to move forward with. If you have any comments or questions, please put that below. Thanks, like, and subscribe.